Good evening. This next lecture presentation will be covering acid-base equilibria. In this first part of the lecture, you will be learning about the different definitions of acids and bases. You will be learning how to write the ionization equations for acids and comparing the strengths of the different acids and bases to each other. There are three main ways that we define acids and bases. The first is by the Arrhenius definition, which says that any acid will be a substance that will produce hydrogen ions in solution, while bases will be any substances that will produce OH- ions in solution. The main form of acid-base definitions that we will look at is the Bronsted-Lowry definition. For the Bronsted-Lowry definition, they define those as the acids being proton donors, which the proton is just a hydrogen ion. If you think about the internal structure of the hydrogen ion, it has one proton, 0 neutrons, and 0 electrons. So it's essentially a proton. So your acids are the proton donors, your bases are the proton acceptors. So when you are looking to define which substance is your Bronsted-Lowry acid or Bronsted-Lowry base, you can look at the chemical reaction that is taking place, and you can simply look and see which substance is increasing in the number of hydrogens. That would be your base, and the substance that is losing hydrogens as you go from reactants to products, that will be your acid. So you can see here the HCl is going to Cl-, so the HCl is losing NH+, which makes it a donor, and the H2O is going to H3O+, which means that it's adding the H+, which makes it the proton acceptor. We have one other definition that we look at in chemistry for acids and bases, which is the most broad definition that we have for all of them, and that is dealing with the Lewis acid-base definition. So for the Lewis acid and base definition, this is based off of the transfer of electrons. So we define a Lewis acid as an electron pair acceptor and a Lewis base as an electron pair donor. So you want to look for the substance that for the Lewis structure has a lot of extra sets of lone pair electrons on it. That would be your Lewis base. The Lewis acid you would have as the electron deficient substance, and so it will be able to form a coordinate covalent bond in order to create a new compound. This is a really big definitional piece for organic chemistry. It is no longer covered in the AP exam, so I'm not going to spend a whole lot of time on it, but I just wanted to make sure everybody knew about what it was. So let's continue our look at the Bronsted-Lowry definition for the acids and bases. So I've set up an example problem here for you where you have HA plus H2O forms H3O+ and A-. When we look at this generic equation, the HA is just any acid and the A- is just the anion that would be present. So when we talk about the initial reactants, we can see in the diagram here that the acid has the hydrogen ion in the bluish gray color, the anion A- in the purplish color, so I'm just going to write in the H+ and the A- here. I have my base being the water. You can see that again. Here's the H and the H and the O. You can see that the water, this hydrogen will cleave off and we'll go to the water, forming the H3O+, and then we have the remaining part, which is the A- that would be left over. So when we look at the products, we have a couple of different terms that we use. The conjugate base is going to be the substance that will remain once the acid molecule has lost its proton. So the anion of the acid, that will be the conjugate base. The reason being, when we go in the reverse direction, the hydrogen ion coming off of the H3O+ would bind to that A- to reform the acid and the water. So the conjugate base substance that remains when the acid has lost its proton. The conjugate acid is going to be the substance that forms when the base accepts a proton. So again, you can think of this, the conjugate acid is going to be the product with a greater number of the hydrogens in its molecule. So I went from 2 H's for the water to 3 for the H3O+, so it's increasing its number of hydrogens. Okay, so let's take a moment to look at a couple of example problems here. So as we go through the first part, again, for A, what is the conjugate base for each of those substances? Again, it can be either an acid or anything that has hydrogens present to begin with that can undergo these reactions. So the best thing to do is to just simply write out what the reaction would be with water. So when I look at this example here, I would have the HClO4. I would react that with the H2O, and it is going to react to form the H3O+, and I would have the ClO4-. I know this is going to be the case because I have HClO4, which is an acid, so it's going to donate its proton. So I can call this the Bronsted acid. This would be the Bronsted base, and then from here I would have my conjugate acid, because again it would give up the H+, and I would have the conjugate base being the ClO4-. So when I look at the second example problem, and I'm going to write that over here on this side. I'm going to do it differently. Let's do this as the H2S, and we place that into water, and it will go to H3O+ and HS-. So again, same type of thing. Bronsted acid for the H2S, Bronsted base for the water. I have the conjugate acid being the H3O+, and the HS- would be the conjugate base. When I go to the next one, pH4 with a plus charge. Now, in this situation here, again, we're treating this substance as the acid because it's asking us to figure out what the conjugate base would be. So as I'm looking at this, I can place that into water. And so now, with that being my Bronsted acid, my Bronsted base, I know that's going to form H3O+, and then I would be left with pH3. So conjugate acid, conjugate base. So conjugate base, conjugate base, conjugate base. Okay, and we have our last one here, the HCO3 with a -1 charge. So again, I'm going to react that with water, and that is going to form H3O+, and then I would be left with CO3 with a 2- charge. So I have my Bronsted acid, my Bronsted base, conjugate acid, conjugate base. Okay, so now as we go through the next set of example problems here, we can look at it in the same type of format, except this time we're solving for the conjugate acid. So now when I set this up, I have my Cn-, I have H2O. So we have a little bit different scenario with these first couple of problems, because if you notice, I have no hydrogens on this initial substance, the Cn- in this case, so I know it has no choice but to be the Bronsted base. The water now will become a Bronsted acid, which means it will give away its hydrogen to the Cn-. So I'm going to form HCN as my conjugate acid, and then I would have OH- as my conjugate base. So the conjugate acid in this case, the HCN. If we do the same thing for the SO4 2-, you guys might be familiar with that and think, oh, it's going to go to sulfuric acid, but they can only ionize one hydrogen at a time. So one of the hydrogens would come over, and that would give me HSO4 with a -1 charge. and then I would have OH minus as the other product. So when I look at this here, again, no hydrogens, can't be an acid, so that's got to be my Bronsted base. Water once again, Bronsted acid, and now from here I can take this as my conjugate acid and my conjugate base. So we have HSO4 minus as the conjugate base. For the next one, now we have H2O reacting with H2O. So now that's going to form H3O plus and OH minus. Very important reaction right here. So we can arbitrarily choose one of the waters to be the Bronsted acid, one to be the Bronsted base. H3O plus would be my conjugate acid, OH minus my conjugate base. And for our last example, we have HCO3 minus. You'll notice in the first reaction, it was going to be acting as a Bronsted acid. We're going to do this next one where it can act as a Bronsted base as well. So I'm going to keep using water as the Bronsted acid. For this, I would then go to H2CO3 and OH minus, conjugate acid, conjugate base. Now, if you were asked a question like this, there are technically two answers, because I could have the, and I'll put that down here, I could have also the HCO3 minus plus the H2O, and it could form H3O plus and the CO3 2 minus, in which case I'd have the conjugate acid being H3O plus and the CO3 2 minus being the conjugate base. And in that case, this would be a Bronsted acid and a Bronsted base. So we'll talk more about the substances that can act as an acid and a base in just a few minutes. The last question, writing the formula for the conjugate acid of each of the following. So we're going to be assuming that these are all the Bronsted bases as a result. Now, you can do this either writing it out the formula, or we know by definition that the conjugate acid is the substance formed when the base accepts a proton. So I could take each one of these and I could just take and add an H plus to it, and that would give me the formula. So for the practice exercise, so if I come over here, the HSO3 with a -1 charge, that would become H2SO3, because again, I'm just adding the H plus to it. The F minus, that would just become HF. The PO4 3 minus, that would become HPO4, and since I added the H plus, it would now become a 2 minus charge. And then I have the CO, so for this one, that would become HCO positive. The strength of an acid is determined by the extent to which it ionizes or dissociates. Ionizing and dissociating are two very similar terms. The end result is the same, where we have ions present in solution, but how they achieve that is different. So for us, you can use them interchangeably. We have a basic reaction for any acid being placed into water, and that will form H3O plus, the hydronium ion, and A minus. When we look at a strong acid, that is going to be one that will ionize close to 100%. So the ionization equilibrium will lie very far to the right, which means it's a very product-favored system. So in this sense, the Ka value for the equilibrium typically is greater than 10 to the 8th power. So you're going to form a very weak conjugate base from that strong acid. You would have only a single arrow, so when we would write the HA plus the H2O, it would have a single arrow to represent the fact that it's almost gone to completion, and we'd have the H3O plus and A minus. So when the strong acid is introduced into water, you would have virtually nothing but the H3O plus and A minus present in the solution from a particulate diagram type of standpoint. There are 6 strong acids which you guys need to memorize. It's going to be different depending on the source that you use. Some textbooks will tell you that if the difference between the number of oxygen atoms and the number of ionizable hydrogens is 2 or greater, then it's counted as a strong acid. But College Board only recognizes 6 strong acids, so I'm going to list them out here for you. So we have HCl, HBr, and HI. Those are your hydrohalics. Fluorine is a weak acid. We'll talk about that later as to why. And then from here we have HNO3, nitric acid, HClO4, perchloric acid, and H2SO4, sulfuric acid. When we talk about your bases, so these again are your strong acids. Your strong bases are pretty simple. You need to memorize these as well. So these will be hydroxides from your group 1 metals. So lithium, sodium, potassium, cesium, rubidium, and your heavier group 2s. So that would be calcium, strontium, and barium. Now, your weak acids, they will only partially ionize, typically less than 5%. So we have the ionization equilibrium lying far to the right. So this would be where we'd have the double arrows. And we would have a little bit of H3O plus and A minus would be in solution. But this is the majority of what we would find in solution if we're looking at a particular diagram. So most of the molecules would be as the HA, not as the A minus. The weaker the acid is, the stronger its conjugate base. Now this is just something I wanted to quickly illustrate for you, just so you can kind of think about what is taking place. Remember, the larger the value for K, the greater the extent of that forward direction. So if I were to look at a couple of different acids, I'm going to do HF and I'm going to do HCN. Now, as a starting point, the HF would go into water and it would produce H3O plus and F minus. The HCN would go into water and produce H3O plus and Cn minus. Now the K values for these reactions, this one here is somewhere roughly around 7 times 10 to the negative 4th power, and the cyanic acid, hydrocyanic acid, is somewhere roughly around 2 times 10 to the minus 10th. So it's a little bit off from that, but it's very close. Now, if I were to look at this in terms of the reverse reactions, so if you think about the reverse reaction and what that means for K, remember, reverse means that we take 1 over the Ka value. So if I did F minus plus the H3O plus, going in and forming H2O and HF, and same thing, Cn minus plus the H3O plus, forming the HCN and H2O. If we do 1 over the Ka, 1 over 7 times 10 to the minus 4th, that's going to be approximately somewhere around 1.4 times 10 to the 3rd. So notice how much larger that is, 1400 compared to the 0.0007. So we know that the F minus is going to do a much better job of accepting a proton because of the fact that its K value for that direction is much larger than the original forward direction where the F minus is a product. And same thing, if I took 1 over 2 times 10 to the minus 10th, we're now talking about having 5 times 10 to the negative 11th power. So, or positive 11th power, or no, 9th, excuse me. So when we would look at something like this, again, very much in that forward direction. So I know that Cn is a much better acceptor of protons than the water is. That's one of the things that you're going to have to do, is be able to compare the strengths of the acids or the bases. The weaker the acid, the stronger its conjugate base will be. You can tell the weakness of the acid by looking at the Ka values. Since hydrofluoric acid, 7 times 10 to the minus 4th, versus approximately 2 times 10 to the minus 10th, you can tell that the HF is a much stronger acid, and so as a result, it would have a weaker conjugate base. We will You can take a look at the diagram here to represent the dissociation or the extent of dissociation that's occurring between the strong acids and the weak acids. So you'll notice I have a bunch of strong acid molecules over here on the left-hand side. I have, in this situation, when this is placed into water, notice I have complete 100% dissociation. I have all my anions as the green spheres, and I have the H pluses as that bluish colored sphere that are there. I have equal amounts of each one. That will typically be the case except for when you have sulfuric acid, our only strong acid that is what we call a diprotic acid, and it can ionize 2 hydrogens per molecule instead. So I'd have twice as many hydrogen ions depending on the concentration. When I look at the weak acid, you can see over here, in this case, I still have on the right side, the majority of the molecules are still showing up as that parent molecule, just like we had over here, but I have a small percentage of them that will actually dissociate. So again, we have partial dissociation taking place. So the majority of the molecules are staying as the parent molecule. So this chart just basically summarizes all the different ways that we can describe the strength of the acid. So the first thing, when we're talking about the Ka value, a strong acid, the Ka is going to be large, again, typically greater than 10 to the 8th. The Ka for a weak acid is going to be very small. The position of the equilibrium constant for a strong acid will be far to the right, meaning that, again, we'll have a very product-favored system. So again, we'd have a large amount of the H3O plus in comparison to the HA. When we talk about the weak acid system, because its equilibrium is lying far to the left, I would have a greater amount of the HA compared to the H3O plus. When we talk about the equilibrium concentrations compared to the initial concentrations, now because we have almost 100% dissociation, you can pretty much assume that the H3O plus concentration is going to be equal to the concentration initially for the acid, as long as it is just HA. When we talk about a weak acid, the HA initial concentration will be much, much larger than the H3O plus or the H plus concentration would be at equilibrium. And then as far as the strength of the conjugate base compared with that of water, again, because we have essentially 100% dissociation, we know that the A minus is going to be a weaker base than the water. Same type of thing, think about that 10 to the 8th as the value for the Ka that we were talking about as a minimum. If we would reverse the direction on that reaction, you're talking about the ability of the A minus to accept a proton being somewhere around 10 to the negative 8th power. So not very good at all. As we look at the A minus for the weak acid, because again, I have a very small Ka value, that means the reverse direction is going to be very large. So the A minus is a stronger acceptor of protons than water. So you saw this previously in our examples that we did for the Bronsted-Lowry definitions of acids and bases, but water is a substance that we call amphoteric, or another name we can use for that is amphoteric. And in either case, that just simply means that that substance can act as either an acid or as a base. You saw the simple reaction of the water reacting with another water molecule to produce the H3O plus and OH minus. This would be a liquid and a liquid, aqueous and aqueous. So we can set up a new equilibrium expression, which is the auto-ionization of water, and we label that as a Kw. Since both the waters are liquids, again, we can take those out of the expression, and that leaves us with the concentration of H3O plus and the concentration of OH minus. At 25 degrees Celsius, the product of these two substances together will always be equal to 1 times 10 to the negative 14th power. Doesn't matter whether it's an acidic or a basic solution. As one changes, so does the other. Now, just a couple of quick things to remember. In comparison, if my H plus is greater than my OH minus concentrations, or the H3O plus, then that would tell me that my solution is acidic. If the OH minus is greater than the H plus, then that would tell me that I would have a basic solution. And finally, if the H plus is equal to the OH minus concentrations, then we have a neutral solution. The last thing that we're going to cover on this initial video is the ionization of different types of acids. So acids will only donate one hydrogen or one proton at a time. So we can classify them as being either monoprotic, diprotic, or triprotic. If I have a monoprotic acid, that is going to be an acid that donates only one hydrogen. So when we look at this first example, we have acetic acid, the HC2H3O2 or O2. This one, the 3 hydrogens that are present that's part of the hydrocarbon, so they are not ionizable. So the only one that can be separated is the initial H. So if I'm looking at this example, I'd have HC2H3O2. I would place that into water, and again, I would have my double arrow since that is a weak acid. It would produce H3O plus, and then the acetate ion, C2H3O2 minus. Now, if you're confused about this with the extra hydrogens here, another way that we can write this is to say that we had CH3COOH. The H that is connected to the oxygen is the only one that is ionizable. So if I would take a structural formula for it, it would look like this. And again, because this hydrogen is connected to the oxygen, the electrons could go to the oxygen here to make it the negative charge, and then I'd have the H plus that would be left over. So this would be my ionization equation for the monoprotic acid. If I have a diprotic acid where I am donating 2 hydrogens, again it occurs in separate steps. So for the diprotic, there's going to be 2 ionization steps. So the first step would take the original acid, so I have the oxalic acid in this case, H2C2O4. I have the H2O. It's going to form the H3O plus, and then I would have the HC2O4 minus. So my conjugate base from this first reaction is going to become the reactant in my second. So I would have that as my new acid. It would react with the water again, and it would form a second molecule of H3O plus, and then it would form C2O4 2 minus. Now, the one thing that I just want to mention, the amount of ionization for each subsequent step becomes less. So each ionization step has a smaller percent ionization. Okay, and that's due to Le Chatelier's principle, having the extra H3O plus still in solution from the first ionization step. So if we look now at the final one here with a triprotic acid, we have H3PO4 as an example for that. So for that first ionization step, I would have the H3PO4, I have the H2O going to H3O plus and the H2PO4 minus. Again, I'm just losing a hydrogen each time. My second step, I would take that same H2PO4 minus, I would react it with a second water molecule, and it would form H3O plus and now HPO4 2 minus, because I've lost 2 hydrogen ions. And then my third step, I would have the HPO4 2 minus react with another water molecule, forming a third H3O plus, and then I'd be left with PO4 3 minus. So we could say that this is Ka1, this is Ka2, and this would be Ka3 for the overall reaction that would take place. You could multiply all your Ks together to get the overall K for the entire process. But again, we know that the Ka1 will be greater than the Ka2, which would be greater than the Ka3, because again, all the extra H3O plus that is present in the solution is going to drive the reaction back towards the left. So you get a smaller amount that ionizes each step. Finally, a polyprotic base. These are going to accept more than one hydrogen ion. Anions with a -2 or -3 charge are examples. So if we're just going in reverse, and I'll just do the HPO4 2 minus, and I react that with water, now it's going to go in the reverse to where I'd have H2PO4 minus and OH. Again, it is a base, so it's going to produce OH minus ions in the solution. So that would be a first step, and then a second step. As it returns to its parent acid, I'd have the H2PO4 minus react with the water again, and it would form H3PO4 plus the OH minus. So that's the end game for the polyprotic bases. It's going to end up returning to the parent acid that it would have originally come from. So let's finish this off with just a quick concept check. Take a moment, pause the video, and see if you can arrange all of these from these bases from the weakest to the strongest and be able to explain your answer. It tells you in the problem acetic acid and hydrocyanic acid are both weak acids. Acetic acid is stronger than the hydrocyanic acid. So take a moment to pause it and then come back and you can look at the explanation. Okay, so as we begin to look at this, key significant parts to this, remember our big takeaway concept: stronger the acid, weaker the conjugate base. Any weak acid, we know that the conjugate base is stronger than water, and as a strong acid, the water is stronger as a base than the A minus, the conjugate base. So as we look at this here, again, knowing that the acetic acid is stronger than the HCN, that would tell me that the acetate ion is weaker than the CN minus. So the CN minus out of these choices is going to be my strongest. So I'd have, there we go. Sorry, my stylus wasn't showing up. So I have CN minus as the strongest, and then I would have the next one being the acetate ion. And now I have to choose the chloride ion or the water. So once more, I'm going to focus on this up here. For a strong acid, water is the stronger conjugate base, or stronger than the conjugate base. So I know my next one would be the water, and then finally I would have the Cl minus. All right, so that ends the first video for acids and bases. The next lecture is going to be covering the pH scale and setting up initial equilibrium reactions and solving for pH from those calculations. So have a good night, and I'll see you in class tomorrow. Bring questions with you.